So I'd like to thank the organizers for inviting me to this wonderful place. I'd also like to start out by saying this is joint work with David Geraghty. In contrast to Sugwoo's talk, this talk was not designed with exposition in mind. Since I'm in France, I thought I would do something unusual and start out with a precise statement of a theorem, unlike my usual talks. But as in Mark's talk, the original statement of the theorem will involve some things for whom the definitions will come later on. Okay. So the main topic of my talk is the following theorem, who, at least in the first way I will state it, will have absolutely no content, but I shall try to increase the content later on in the talk. Okay. So let F on Q be an imaginary quadratic field. Let P be a prime bigger than 2, be unramified in F. Let E on F be a semi-stable elliptic curve with ordinary reduction at places dividing P. So let me now suppose that the mod P Galois representation associated to E, so this is a representation of GF, which is the Galois group. Did I say good? No. So it could be good, it could be bad. Okay. Suppose that this representation GL2 FP is modular. That's something which I'll have to define in a moment, so let me now just underline the word to indicate that it's not so well defined. And that this representation has big image, namely that its restriction to the Galois group of F with the pth roots of unity is irreducible, well, absolutely irreducible. Okay. Well, it could be 1, it could be 2. Yes, ordinary at both. Yes. Okay. Assume conjecture star. Then E is modular. Okay. Well, for appropriate values of star, this is an easier or harder theorem. I will explain what conjecture star is, but let me now give you the cartoon version of what conjecture star is. Is that ordinary implies ordinary. That's how I'd like to say it, because it sounds easier that way. I'll say something more precisely later, but ordinary cohomology classes give rise to ordinary Galois representations. Okay. So I'll explain. That's just a cryptic summary of what the conjecture star is, but I'll be much more precise momentarily. So I should say I don't know how to prove this conjecture, and I don't know how hard it is, but it's probably not something. It's something for an expert, and the expert is not me. So let me make some remarks about this. I will be precise about what I mean by that. So remarks. So certainly the case that PGL2 F3 is S4, and one has automorphy of, for example, complex Gauss representations from GF to GL2C with projective image S4 by Langlands and Tunnel. However, if F is not totally real, this is of no use to prove that rho bar is modular. In the case of rho EP, well, say E3 is modular. In the case of F is equal to Q, there's the trick of Wiles, which by using this result, and then using the fact that weight 1 modular forms were congruent in a suitable sense to weight 2 modular forms, allowed you to use this result to prove the hypothesis that rho E3 was modular in many cases, and therefore to deduce that semi-stable elliptic curves under some conditions were modular. But that can't possibly work in this case. I mean, it would be a bit like saying, if you had an even Gauss representation and you knew that even Gauss representations were modular, then you can consider it, is there a congruence mod 2 with a modular form? And there's no relation between mass forms and modular forms in any direct sense. And in this case here, the automorphic form that you have has no cohomological interpretation, and so that you can't relate it in any way to what's going on here. Okay, that's one remark. Maybe here's just another remark. So there's at least some cases for which one can establish the hypothesis. For example, you could take P to be 3 or 5 and assume it was unramified in F. And then you could let A on Q be an elliptic curve such that rho of AP restricted to G F zeta P is absolutely irreducible. I haven't told you what modular is, but it's certainly the case that if you take a representation that's modular over Q and restrict it to F, it will still be modular. And so in particular, you can see there exist infinitely many elliptic curves E over F whose J invariance is not in Q, such that, well, E is semi-stable. Maybe I should have assumed A was semi-stable as well. E is semi-stable, and EP is isomorphic to AP restricted to GF. And so therefore the theorem would apply to such elliptic curves, just using the fact that X of P, the modular curve, has gen as 0 for these small primes. So there are at least some examples for which this can apply to, but it's still not a particularly, I mean, even with the conjecture, it's not quite satisfactory enough to sort of be completely useful.
Just remark, so somehow the point that even though in this case you would have like this weight 1 form and weight 2 form, there's no systematic way of like getting congruence. So even though you do conjecturally
yes.
things which are congruent, there's no way of kind of doing that a priori.
Yes. Yes, indeed. Okay. So some definitions. my chalk is running out. Let O be the ring of integers in a finite extension. Ring of integers in some finite extension K of QP, finite. Choose some uniformizer and let K be the residue field. And for all purposes, usually in arguments, one wants to sort of increase the size of K so it includes all eigenvalues of various representations. And so K is just going to be big enough for all purposes that are necessary. Okay. So I have to say a little bit about what it means to be modular. So what does Langland say about where conjecturally should one find the automorphic form associated to, say, a motive of or elliptic curve over an imaginary quadratic field? Well, there should be some regular algebraic automorphic form for GL2. This form will be of cohomological type, and so it will contribute to the cohomology of the corresponding locally symmetric space, which in this case will consist of hyperbolic 3 manifolds. Okay. For matters of convenience, I'd rather work with PGL rather than GL. So, let AF be the finite Adels, and let K be some suitable compact subgroup. And so the type of manifolds or orbifolds one is interested in just have the usual form times, running out of space, mod K. So what type of things, what do these spaces look like? Well, here for H, this is hyperbolic 3 space. And you can write Y as some just finite disconnected union of quotients H mod gamma I, where gamma I will, so gamma I is commensurable with just GL2 OF. Okay. Just because working with disconnected things is slightly annoying in terms of the arguments that I will make, I would just like to make a simplifying assumption, namely, for example, that the class number of K is 1, just so instead of working with some union of spaces, I can literally talk about single quotients, and I can talk about group cohomology instead. So just for convenience, at least for many K, I'll just consider quotients of this form, and in which case, since H is contractible, the homology of Y will just be the same as the homology of the corresponding group, and similarly the homology of similarly the cohomology. Okay. Implicit in this, of course, it can be the case that these Y are actually orbifolds, and so when I talk about the cohomology of an orbifold, I really mean in the orbifold sense, which you could interpret as just being whatever is correct to make this correct. Okay. Okay. So in the usual way, these groups admit an action by some Hecker operators. So, well, let's work in this context, since we're thinking about elliptic curves, what's the appropriate cohomology it should correspond to? It should correspond to either H1 or H2 with just coefficients over the complex numbers. So these are the cohomology groups we're interested in, but of course we want to think about them integrally. So you might imagine that, for example, we could take the cohomology, say with coefficients in O, and then you might try to define T by just taking the O algebra of endomorphisms generated by the Hecker operators. That's an okay definition. What's slightly annoying, though, is that you would like to take these cohomology groups and, well, reduce the coefficients mod p to the n. And it's not clear, even though that the action of the Heck operator by this ring on that will still necessarily sort of subject onto the appropriate thing. So the correct definition is to take the ring of anamorphism somehow acting on this, but also acting on this with coefficients mod p to the n for all n. So just the union over n. I mean, conjecturally, these should probably be the same. And in general, this will only, at worst, be slightly bigger than this. But this is technically just the more convenient definition. OK, so T is a finite O algebra. And the key point, it's not torsion-free in general. OK. All right. So now let M inside T be a maximal ideal. And let's assume that the residue field is K, and we could always increase K for this to be true. The first one is a question mark, which is this is a plausible definition, and the next one is a tick, which is this is the actual definition. Yes, it's just the O algebra generated by the usual Heck operators acting in the usual way. I mean, just in terms of double cosets. Hmm? To avoid subscripts, because lots of different Heck let's just obscure that point. Let's include the one at P for the moment, the ones at times dividing P, which will certainly be true for, yeah. OK. So then one has the following theorem, which is certainly a special case of result of Peter, and also we saw in yesterday's talk, is that there exists a Galois representation, rho bar, associated to M from GF to GL2 K, with the property that, or the expected property, that the trace of Frobenius at a prime V not dividing the level of P is equal to TV mod M. Okay, for say V not dividing some level of K and P. Okay. What's my other definition? Well, I mean, I just choose. I mean, I should say let. If I say suppose, then I'm now consistent. Yes, well, that field K will never appear again. So you can call it E if you like, since the elliptic curve is also gone. OK. OK, now, in fact, one would like, in fact, not merely to have this Galois representation, but also Galois representation associated to the whole Heck algebra. And this is, in some sense, what one has, with some caveats. Namely, let's suppose that this representation here is absolutely irreducible. Just to avoid issues with pseudo-representations. And since we're interested in modularity, this will always be an assumption anyway, so it's not really a problem. That's just the level, some measure of the level. I mean, just you could, the set of primes for which KB is not maximal, compact. I mean, some finite set of primes. Okay. Okay. Okay, so continuing in this theorem, one has more. So, as I said, if rho bar m is absolutely irreducible, so there also exists, well, an ideal I inside T, and now let's say we complete T at M. So we have this ideal with, well, I don't know the exact number, let's just say I to the 10 equals 0. And a Galois representation, rho m, from GF to GL2 Tm modulo I. Okay. Oh, with the, yeah. So the trace of Frobenius, again, for all but some finite many primes, is still TV mod I. Okay. All right, so of course, this is an absolute necessity in order to start trying to prove some modularity. Result is to actually have Galois representations associated to torsion classes. Okay. It's an ideal. 10. Yes. 9 plus 1. Okay. Well, I mean, there's some actual number in Peter's paper. I'm not going to remember it. Yes, maybe even less than 10. Okay. All right, so now I can define some of the terms in my statement of the theorem. So let's suppose we just take a representation rho from GF to GL2K, well, be absolutely irreducible. And let me also, just for convenience, assume that rho bar restricted to dV is of the form the cyclotomic character here chi unramified epsilon cyclotomic. Okay. Okay, so here's the definition, is then this representation is modular if there exists an M in T such that this construction, rho bar M, gives you back rho bar. So you might view this as a weak set conjecture, but I want to make a strong set conjecture, namely that in this construction of T, I had to choose a specific K, a specific level. So here where K, well, let me just write it this way, and you can guess what this might mean, is K0n, where here n is the usual definition of the Serre conductor of rho bar, and n star is just taking into account whether you have to include the primes dividing P or not, which has to do whether this is Po or Tre or Mifide. Okay. So let me just make one remark about this definition. That's inauspicious. Let me make one remark about this definition. So it could be the case that the cohomology groups H1 and H2 in characteristic 0 are just trivial, but that maybe integrally give you something like FP. If in that case, certainly this T would be non-trivial, there would be a corresponding Galois representation. So in particular, the implication this is modular does not imply that there exists an automorphic form of this level, but merely that there exists a torsion class in the cohomology of this hyperbolic 3 manifold. So that's certainly a much weaker statement, and the more general statement would be false in general. Well, the general statement that any two-dimensional absolutely irreducible representation is modular satisfying these properties is modular is false. In general, if you insist for a characteristic zero lift. Okay. And let me also say what it means for E to be modular. Okay, so E, this is modular. Well, one way to think about it, one definition, is if there exists a map from this Hecke algebra to O, which sends TV to AV is 1 plus the norm of V minus the number of points of E over FV, at least for V prime to the conductor and P. And one implication of this definition would be that the Hasse-Weil L series of E would be equal to the automorphic L function of some pi for GL2 of some very specific kind, regular algebraic, with some weight, well, corresponding to the appropriate trivial local system. Okay. Now let me return to this theorem. So if you're thinking about Gauss representations associated to automorphic forms, or more general to torsion classes, you would like not merely that it satisfies compatibility with the action of Hecke operators at primes away from some finite set, but you would.
Can I just ask one thing? So before you mentioned there was the difference between the expression mark and the tick,
Yes.
the two definitions of T.
Yes.
So when if you have a map from T to O, this definition, you still get pi.
Sure. Yes, if you have an elliptic curve over Q, then it will give you there is a base change form, and it will be modular in the sense. Yes. Yeah. That's a very good question, and the answer is absolutely not. I mean, if you could, I mean, of course, a weaker version of this theorem that I should mention, thank you for mentioning this, if you have something in characteristic zero, then already a previous theorem of Harris, Sudri, and Taylor constructed the Gauss representation, but that construction was by a very involved route, and did not in any way proceed by constructing some motive. So the existence of, say, some motive that you expect associated to these automorphic forms is certainly completely an open question. So.
Can you say a little more about why is that clear?
Yeah, well, I mean, these rings are finitely generated O modules.
My question was just, there seems to be some tension because on the one hand you have this question mark and the tick definition of T, right? On the other hand, when you have like T mapped into O, you still get a pi.
I mean, these rings are the same up to P torsion, for example. Okay. Okay, so what one would like to do is to say something stronger about these Gauss representations. So one can hope for an extension of Schulz's theorem by the following three ways. Namely, one could hope to improve Schulz's theorem in three ways. So one is that this rho m satisfies local global compatibility at primes V not dividing P. Two, well, one could ask to satisfy local global compatibility at V dividing P. And three, one could hope to take I to the 10 is equal to 0, and then cancel the 0 and get I to the 1. is equal to 0. Okay. So, assuming 1, 2, and 3, in a previous paper of myself with David Geraghty, we proved a minimal modularity lifting theorem, a minimal modularity lifting theorem. Okay. Yes? Yeah, I mean, in this definition, I think you can obviously change it in a way that would be satisfactory to you if you have a complaint. Well, that's a good question, and let me get back to that in a moment. So let me say a few remarks now about these three. So condition 1, at least to the extent that it's needed for our purposes, this was essentially resolved by Ilovama in her thesis. So that's no longer an issue. The third point, well, there are certain ways to avoid it, to maybe remove it in this case, but nonetheless, this is not essential for the method. So in particular, we don't need to assume anything about that. Some nilpotent ideal is fine. Whereas 2 is important, and 2 is not something we know how to do. And so conjecture star is essentially 2. Let me say a little bit more about what it means. What do 1 and 2 mean? Well, without going into the complete details, for example, you could imagine if the level of k at a prime v was of the form gamma 0 v, that the action of inertia at v was unipotent. So there's natural things you could write down, and so these things are certainly true. So what about for 2, local global compatibility at p? Well, I mean, it's maybe slightly annoying to phrase it in the most precise way. So something that we prefer to do is work in the ordinary case, just because in the case of ordinary cases, it's fairly easy to say what it means to satisfy local global compatibility. Namely, if TV for v dividing p is a unit, then you would hope that this Gauss representation locally is reducible. It's extension of the cyclotomic character. Has this form, but now this character on Frobenius takes the value t. Okay, so that's what local global compatibility would be in the ordinary case, and that's exactly what conjecture star is. Okay, I mean, you can be more ambitious, but one reason to phrase it is that maybe the local global compatibility in the ordinary case might be easier than in the most general format. Okay. Great. I need to erase some boards again. Okay. So we have the following sort of general structure. Right, so when I say in the minimal and non-minimal case, what am I referring to? Well, we have our elliptic curve, which has some conductor n, but we also have the mod p representation, and it's quite possible that the mod p representation is less ramified than the characteristic zero version. Namely, it's quite possible, for example, with an elliptic curve, which has semi-stable reduction at L, but when you look at the mod p representation, it's unramified at L. Okay, so we can let, say, the conductor of E be equal to something S times, times the Serre conductor of rho bar with the appropriate factors of P. Okay. And so the case S equals 1, this is the so-called minimal case, and this is what was answered previously in our previous paper. But in order to explain the the more general case, I need to sort of remind you or tell you a little bit about what the method was in the minimal case. So let me first just give a very potted version about what one has to do to prove modularity results, even just in the usual context, say in the context of whiles. So what you have is a tension between two types of objects. You're looking at a Galois deformation ring, and you're looking at a Hecker ring. And a priori, you only have very limited control. On the one hand, on the Galois deformation ring, you have some kind of control over the tangent space. And on the Hecker side, well, maybe you know it's non-zero because you assumed rho bar was modular. And so what you do is you patch things in a certain way such that if you allow extra ramification of both sides, the Hecker algebra gets bigger and bigger. And yet, because you're choosing your primes in some careful way, the deformation ring, even though it's getting bigger, its tangent space is not getting any bigger. And in the end, you sandwich your say your deformation rings and your Hecker rings. This is some ways such that by patching you have so many automorphic forms that you get so many Galois representations that this object here is very big. On the other hand, you've controlled the size of the tangent space, so you have an upper bound on the dimension. And then you can observe that the dimension of this is at least the dimension of this. And since, for example, at least in Weil's case, this is smooth, you get this is the same, and you have enough control to be able to deduce something at finite level. So what's clear in the case of imaginary quadratic fields is that, well, you need to somehow show that the Hecker algebra in some patched way is big. But there's an issue of what does big mean? So in this classical context, there's an action of some auxiliary ring, which is a ring of diamond operators, which is just some algebra of this kind. And typically what happens is that all these three objects have the same dimension here. So what happens in the case of imaginary quadratic fields is that the Galois deformation ring is actually smaller. When you do this patching, the number of variables required here, is, at least in the smooth case, is one fewer than here. So you have to prove that T is big as a module over this ring, but you don't have to prove, you're not trying to prove it's free, because that would be bigger than is possible. You want to somehow prove it has codimension 1. Well, so how does Wiles, for example, prove that it's free in the case of the classical modular curves? Well, what happens is that all the cohomology is occurring in 1 degree. And so when you start taking, after you localize in a maximal ideal, and so once you start taking coverings with all the cohomologies in 1 degree and you take a cover, essentially the cohomology of that cover is forced to be free over the corresponding group. Well, I'm kind of obscuring some details here, of course, but what happens in this case? Well, in this case, we have cohomology in 2 degrees, namely this H2 and H1. Okay. And for example, well, of course, there's H0, but if you localize at M, this disappears. Okay. So depending on rho bar, you find infinitely many sets of Taylor-Wiles primes, Qi, I equals 1, to Q. And then you look at the cohomology groups at some augmented level. Well, let's call it level gamma H of Qn. And you have to look at coefficients, mod maybe some power of n. And then you have H1, gamma H, Qn, pi d. Okay. All right. So what you're doing is you're increasing the level in some sort of controlled way, and you're hoping to obtain more cohomology. So certainly in characteristic 0, you kind of get nothing. Even if you have 0 to begin with, you can see the Euler characteristic is 0, and so the Euler characteristic of some cover is also 0, and you don't get any apparent cohomology growth. So what is it that's controlling the cohomology here? Well, previously, if you have cohomology in 1 degree, you could imagine, very loosely, the cohomology is computed by a complex which just has a single term, and you get something that's free. So what you would like to do is to show that these cohomology groups are computed by a complex just of length 2, and if you've got a complex of length 2, well, then you can hope to see that the cohomology of this complex is maybe of codimension 1. Well, of course, what is the appropriate ring we're dealing with here? At this level, we're looking at various rings which are of the form O, even mod pi to the n, times z mod p to the n z to the q. And these rings certainly don't have a good notion of codimension. But what happens is when you patch everything, and now I've doing well for time. Okay. Pen again. So essentially by what you could call, by Taylor-Wiles patching, you obtain a complex P. Well, it just has 2 terms, and these are of free, finite, S infinity, Y1 to YQ modules, such that, well, essentially, the cohomology of this complex is the inverse limit of the cohomology of these finite terms. So, for example, yeah, this is built in such a way that the cohomology of this complex tensor down to this of S infinity to this finite ring Sn are just these cohomology groups at finite level. Okay. Okay. So now you have a complex, and you have some action of this ring S infinity, and you want to prove, again, that this T infinity is big, namely it has codimension 1. And so basically, well, you want to look at the cohomology of this complex, and what happens? Well, if this map is has some kernel, then the kernel is a submodule of something free, and so it has codimension 0. And so if that happens, then T is so big that it's bigger than R, and you get a contradiction. So, in fact, this complex has to actually be a resolution of the final term, but it's a complex of length 2 of some very nice ring. The quotient has codimension 1. So you deduce that the patched modules you get are sufficiently big to imply that they're as big as R, and to deduce some R infinity equals T infinity, and to go back down to finite level. Okay. Okay. So one thing that's going on that's very convenient in this argument is that this ring R infinity is smooth. And what's nice about that is to show some equality, you really need to check just in some sense that T is big enough. In the kind of more general kind of Kissen version of modularity, you have to take into account some local conditions, and your R infinity is no longer smooth. In particular, it could have more components even when you invert P. And then by this method, well, you might still deduce that some of the components are modular, but you don't necessarily hit all the other components. Okay, so that's somehow a difficulty. So the issue is how to prove non-minimal modularity lifting theorems. So let me just give 4 different ways to try to prove, 4 different things that are done, not necessarily in historical order, but 4 different ways of proving non-minimality. So one, just by the general Kissen method, you're reduced to showing that on each local component there exists something that is on the T side. And so what you might try to do, or what one does nowadays, is you use the so-called Carré-Winton-Béget method to produce sort of lifts, global lifts, with the correct local properties. So there's two problems with this method in the case of magic quadratic fields. One is that formally it doesn't work, and two, it's not true. So in general, I mean, all these things are built out of torsion classes, and you don't even necessarily expect there to exist some global actual characteristic zero automorphic form that hits those components. So that doesn't work so well. So two, well, there's the Taylor's Ihara avoidance method. And one thing this does is move things around so you have some other deformation ring that still has one component. But this is not so good because this requires base change. And I certainly don't know how to prove anything like base change for torsion representations. And even if you did, there'd be other technical problems that would cause you. Because you have to, your primes dividing S, you have to have the fact that they're one, the residue field has some certain property. Okay. So three, well, this is maybe going back to the first approach. There's Weil's numerical criterion, for example, is modified by faultings. So here, you want to compare some minimal deformation ring to some deformation ring at higher level. But here is just some nice piece of commutative algebra that at the very minimum requires these rings to be flat and finite over O. And essentially, even though I tried to find some modification that would work in this context, doesn't seem to sort of be useful. I mean, these things are certainly not finite over O in general, they're certainly not Gorenstein in general. So it's something quite different. So that doesn't seem to work. And four, here's another technique that was in the papers of Kissen. So you could, for example, pass, say, via Jacquet-Langlands to a context in which, say, we want some conditions, we want to look at local deformations that are Steinberg at S, such that Steinberg at S is the same as the minimal case. Okay. But again, there are some problems here. So in order to do this, well, for parity reasons, you need some kind of base change, but you also need a Jacquet-Langlands correspondence. So in my work with Akshay, we do prove some Jacquet-Langlands correspondence for torsion classes, but it's far too weak to be useful. It's only a numerical correspondence rather than a Hecke equivariant correspondence. Okay. But nonetheless, this is sort of representative, perhaps the closest to what one actually wants to do. Okay. So, well, the first idea is to work instead with the arithmetic group gamma 1 on S, namely subgroups of, say, PGL2 OF, where you invert here. So what does the cohomology of this look like? Well, again, unlike in the case when S is trivial, I mean, you can construct spaces which have essentially this as their pi1, but they're not manifolds, they're somehow more complicated objects, but nonetheless, there are still things one consider in the group cohomology here. But in characteristic 0, what you find is that the relevant automorphic forms, I mean, in characteristic 0, you see automorphic forms for GL2 that have some particular local conditions at S, that they're Steinberg, essentially. Is that in characteristic 0, automorphic forms contribute to the cohomology of gamma 1 on S in degrees m plus 1 and m plus 2, where m is the number of prime divisors of S. Okay. Moreover, you can show that even in the torsion cohomology, it vanishes in degrees above m plus 2. So really the key part of this method is to show that all the cohomology is just occurring in 2 degrees. So ideally is what you would like to show is that the cohomology of this group only occurs after localizing at m in degrees m plus 1 and m plus 2. So what I like to do is to prove the result in the case when m is equal to 1, and then m is equal to 2, and then m is equal to 3. These are all different, but the case that m is equal to 3 will be the one that sort of generalizes. Okay. Okay. So, well, how is the cohomology of this group related to the cohomology of just the more classical arithmetic group? Well, here one uses just a very special fact that we really have essentially the group PGL2 or sort of SL2 rather than SLN. Namely, these groups can be actually written for each additional prime as an amalgam of lower groups. I mean, this is in fact going back. I mean, we're really looking at a question related to level raising, and this is exactly how Ribbett first proved level raising results to begin with, using the fact of amalgams and the congruent subgroup property. Okay. So if you write S equal QT, then your lattice, if you invert S, is essentially an amalgam of gamma 1 on T and gamma 1 on T along the group gamma 0 Q 1 on T. Yeah, it's an amalgam of 2 groups. So you have a group, both these groups have a copy of gamma 0 Q, one with a 0 in the lower corner and the other in the sort of upper corner. And if you glue them together along those 2 different things, you get this loop. I mean, amalgam, you start with 2 groups. Yeah, yeah. So this is SL2 and this is SL2. This has a subgroup which is 0 mod P, and this is a subgroup where this is 0 mod P. So if you take the free product and identify this with this, you essentially invert P. Okay, wasted valuable board space there. Okay, no. Okay, so you get a long exact sequence. Well, you start with, see here, H3. So let's just take the case where m is equal to 1. So the first term is H3, then H2 gamma 0 Q, then H2 gamma squared, then H2 gamma 1 on Q, then H1 gamma 0 Q, then H1 gamma squared, and then H1 gamma 1 on Q. And if you localize at m, well, you kill off the H0 terms. And so you have an exact sequence of this kind. All right, so what you'd like to prove is the cohomology is occurring here and here, so you'd like to get rid of this term. But in fact, you can, just by using the same as Ribbett's proof. Namely, this group satisfies the congruent subgroup property, and so you can simply compute this group, and it's just literally Eisenstein, and so this disappears. And that shows that all the cohomology is in these 2 degrees, and that's enough to essentially give you the proof that m is equal to 1. Okay. But m is equal to 2 is going to be different. Okay, so now that m is equal to 2, okay, well now you get a similar exact sequence, except now you're starting with H4. Let me say, just write Q and Q prime. Let me leave out some of the terms. And here, H2 gamma, say 1 on Q prime squared, mapping to H2 gamma 1 on Q prime. And again, we localize everything at m, and our coefficients are probably just O mod pi to the k. So again, we have our h4 and our h3, and we'd like this h2 to be 0. The conclusion here is this h1 vanishes, and so all the cohomology is occurring in these 2 degrees. And that's the key point to get this method to work, because you want to patch and have something of codimension 1. And now that you're working with the group gamma 1 on Q, things are automatically Steinberg, and so you have the appropriate local condition. I should say you have to, in these arguments, you actually increase the nilpotence of the various ideals. Well, m was equal to 1, so t was equal to 1. Yeah. Okay, so what you like to do is to show this is 0. But now you have h2, and of course, this is a bit more tricky because there's no congruent subgroup property. In fact, in my paper with Akshay, this group, essentially, well, at least it includes some part related to K2 of this number field. And it's very hard to kind of say something about this. I mean, it's analogous in some sense to the problem of trying to control H1 of a quaternion algebra when you invert P. Of course, you expect the congruent subgroup property to hold, but since you can't prove it, for example, Richard Taylor and Fred Diamond went to a lot of effort to sort of get around this problem when they were doing something similar. So you have some difficulties. But one thing you could observe is that it's a quotient of this group, and so the corresponding Gauss representation here will be unramified at Q. On the other hand, it will also be unramified at Q prime by exhibiting the following, by just replacing the order. So on the one hand, this is unramified at Q and Q prime. But it's also Steinberg at Q and Q prime. So that's quite peculiar. It namely says that the Gauss representation has some very specific form locally, and something that even cuts down the corresponding deformation ring by some large amount. So what happens is, when you do the appropriate patching, you get a complex of length 3, and then you see what happens. Well, the kernel here has to be trivial, because otherwise it would have codimension 0, and you would win. So what happens here? Well, if there's some cohomology here, you'll be forced to have codimension at most 1, and that will be big enough to show that the R is equal to T. So if you're trying to prove something, you can assume that essentially there's no cohomology here and there's no cohomology here. Because if there's cohomology here, you win. So you're left with worrying about everything sort of being sucked up into this term. So on the one hand, I mean, the fact that it's this complex of length 3 over this nice ring, you can deduce from this that the codimension of the cohomology is at most 2. But on the other hand, this is not so useful compared to the size of R, because R, its size, the dimension looks like it has codimension 1. But on the other hand, you know it's Steinberg and unramified at Q and Q prime, so the appropriate deformation ring has now gone from something which had codimension 1, but there's 2 further conditions that you get here. So in other words, the cohomology acting on the, the action of the R infinity on the cohomology of these 2 pieces is factoring through R infinity, but on the quotient is acting through something much smaller. So even though the cohomology here, you don't deduce it's big enough to get an immediate contradiction, the action on R is through something much smaller, which is enough to get a contradiction. Okay. So that concludes the case of m is equal to 2. Okay. So let me finish with the case of m is equal to 3, because that m is equal to 3 is going to be the case for which things will generalize. Because now, you see, what's happened is we haven't proved this h2 is 0. We've just proved it somehow moderately small. But it's still going to cause an annoyance in the next cycle. So, well, here m is equal to 3. Here we start with h5, q double prime. So what happens? So what are the key terms here? There's h3 we want to show is 0. Q double prime, and there's also h2. 1 q double prime. Okay. So as before, you can patch and get a complex p5, p4, p3, p2. So this has to be injective here, because otherwise I have codimension 0. If there was cohomology here, it would have codimension 1, which is enough to get R equals T. So now you have to worry about this term here and this term here. So what would happen this term here? Well, this could have codimension. If something happens, it has codimension at most 2. So the question is, well, can you say anything about H3? We can no longer say it's certainly, for example, there's a map from here where one of the primes is gone, but there's still a piece on the other side, which is namely the H2 of gamma 0 Q double prime 1 on Q Q prime. So the quotient here is unramified, but there's another piece here. On the other hand, if you patch this entire sequence, you can divide the patched H3 into 2 pieces. One is the image of this, which will be unramified at all, one part will be unramified at all 3 primes, and another part, which will be coming from here. And what happens is we already saw previously this had codimension at least 3, and the image here will the other parts will somehow be unramified everywhere. Well, of course, you shouldn't just take one thing. You should take the kernel of this map to all 3 of them at once. Okay, and the image will have to be unramified everywhere. So this will be sandwiched between a piece that's unramified everywhere and this piece, and so the codimension is at most, well, there's 3 from the quotient, and then unramified everywhere is 1 plus 1 plus 1 plus 1, which is 4. Well, not 3 plus 4, but 3 or 4, which are both, fortunately, bigger than 2. And again, the final term here, unramified, right? So now we know that this has to be exact here and here. This final term, it has codimension at most 3, but now it's unramified at 3 primes, and plus the extra 1 coming from that. We see that this has to have codimension at least 4. So to say something more general, if I somehow define Hi just to be the homology of this complex, what you can prove is that, well, is that the codimension of Hm minus I is at least, right, you want to show that Hm, you'd like to vanish, but in order for not to interfere with this argument, you want to show it's at least something like 3 plus I. Yeah. And so by an inductive argument, you get this. And this is just exactly enough to not interfere with this argument. Rather, if there was no cohomology at the point which would have modularity, you don't show these things as 0, but they're still too small to sort of exist as the cohomology of this complex. Okay. I should probably stop here.
If you could incorporate something like a U operator into the construction that's used, well, in the construction of the Gauss representations attached to torsion classes, would you be able to localize and then show the ordinary property is preserved?
Would I? Probably not. Would someone in this room, possibly?
Your co-author, maybe?
I mean, the reason, of course, you didn't, where was ordinary coming to this argument? Of course, it was just being absorbed by these deformation rings. If you had finite flat instead, everything would be exactly the same.
Yes, but the ordinary, there are other methods.
Well, that's why I hoped that was, I kind of hoped it was going to be proved before I gave the talk on this theorem, so I could sort of remove the star. But I mean, I'm not I expect it to be proved in the next 5 years if I was a betting man, which I am. Bottle of champagne. Mark will buy me a bottle of champagne if this theorem is proved in the next 5 years. But it's somehow just not exactly the type of...
Well, there are people who specialize in that sort of thing.
Well,
I know some of them, in fact.
Yeah, we can talk about this afterwards.
Any other questions? Remarks? So we thank Frank again.